Let's begin. Now, last class we looked at some important classification of differential equations, right? The first classification was if the differential equation is an ordinary one or a partial one. We said that a differential equation is an ordinary differential equation if the unknown function has only one variable. And differential equation is called a partial one if the unknown function has at least two variables. So you'll have the derivatives with respect to, let's say, x, and with respect to, let's say, t or y. That would be at least two variables. Okay. We also talked about the order of a differential equation. We defined the order of a differential equation as the highest order of the derivative that you see in the derivative itself. Now we'll continue a little bit further, in terms of the classification of differential equations. Classification is very important because as of next class we'll start talking about solutions of differential equations. But the technique of solution that you'll be using will heavily rely on the type of the differential equation. So if you cannot classify it in the first place, you will not know what to do later. That's very important. Order, again here n is a positive integer, so it can be 2, 3, 5, 1, whatever. Okay? And nth order ODE is called linear if it has this form. So a linear and ordered differential equation will be like this. Let me write the whole in this. It is up to a1x y prime plus a0 x y equals x. So the general format of a linear differential equation is this. It's going to be some function of x times the nth derivative plus some other function of x times the n minus first derivative. You go this way up to some function times y is equivalent to some other function. And here, all of these coefficients are some functions of x. Again, you do not impose anything, like in terms of continuity or differential, they can be any functions. Now, in particular, if n is 2, for example, this is important, you'll have a second order ODE, and it will have this form, a 2x times y double prime plus a 1x times y prime plus a 0x times y equals bx. Okay, so this is second order linear ODE. I'll make a request for a bigger classroom if possible, so that everyone can sit down. If n is 1, then you'll have something like this: a 1x y prime plus a 0x y equals x. So this is a first order linear ODE. So for example, if you look at this equation, okay, you have sine x times y triple prime minus cosine x over e to the x times y prime is equivalent to tangent of x. This is a linear differential equation, right? Because you have some function of x times the derivative of y, like third derivative, and plus some other function of x times, again, some derivative of y is equivalent to some other function. So it's a linear one.
Y is a derivative, just like a normal derivative, or a derivative like this?
No, when I say y prime, it means this normal derivative. This means dy dx. By the way, this is linear. It's an ordinary differential equation, obviously, because you have only one unknown. You have only one variable, and the order is 3. But if you look at the other two, these two are non-linear. Okay. Why is the linearity has been violated? Well, here because you have y prime squared. What does it mean? It means you have y prime times y prime. If you look at this expression, you do not see anything like that. In a linear differential equation, the unknown function and their derivatives are all separated from each other. You do not see them together. That's because of this term, this is not linear. In the second one, this is not linear either. In this case, because of this term here. you are multiplying y with its third derivative. Okay? Because of these two terms, these are non-linear. In other words, in a linear differential equation, you'll never see, we do not have any product, any ratio, any sine, cosine, any exponential, etc. All sorts of functions of y, y prime, y double prime, etc. In other words, if in a differential equation, if you see a term like e to the y, then this is not a linear differential equation. If you see a term like, let's say, sine of, let's say, y plus y prime, it's not a linear differential equation. If you see something like, let's say, y over y prime, it's not a linear differential equation. You cannot have any product, any ratio, any trigonometric function, any logarithm or exponential of y and its derivatives.
So the first example, it was sine y.
If it was sine y, yeah, it would be non-linear. Now I'll have one final remark before we keep going. This is actually something related to what we talked about last class. Remember, when you have a differential equation, when you have a solution, you always indicate an interval for the solution, right? Now, say that you have a differential equation, and you not only want to find a solution to the differential equation, but you also want to plot the graph of the solution. Now, here you have to be very careful. I want to explain this over this example. Now, I claim that this function, y equals 1 over x, this is a solution of this differential equation. X times y prime plus y equals 0. And this is very easy to check. I will not write the details, but you can write it at home. Like it will be x times the derivative is negative 1 over x squared plus 1 over x. It will be really 0. So this is a solution. But now say that you want to sketch, right, the graph of the solution. And you all know the graph of y equals 1 over x. The graph of y equals 1 over x is that you have a vertical asymptote at 0 and x-axis is a horizontal asymptote. Like, vaguely speaking, let's remember calculus 1, right? It's like this. This is the graph of y equals 1. But is this really the graph of the solution? Now, whenever we talked about, as I said, the solution of the differential equation, you need to have an interval. The interval is either given to you or you choose it in such a way that your function, in this case this, and its derivatives are continuous in this interval. Now in this case, the function is 1 over x, its derivative is negative 1 over x squared. Both of which are problematic when x is 0 because you get 0 in the denominator. Therefore, when you are choosing the interval of solution, you can choose any interval, but you have to make sure that 0 is not in the interval. So you can choose any interval not containing 0. Clearly 0 is not in the interval of solution for the reasons that I just explained. Now, say that you picked the interval of solution to be the interval from 0 to infinity. If that's the case, then the graph of your solution would be only this. That's because you're looking at the interval from 0 to infinity. If you picked the interval of solution as the interval from, let's say, negative infinity to 0, in this case, the graph of the solution would have been this. The solution interval doesn't have to be an infinite interval. It can be even a small interval, let's say from 3 to 10. So here is 3, here is 10. So between 3 and 10, the graph of the solution would be something like this one. This is the solution. So my point here is, whenever you have a solution to a differential equation, it's not necessarily true that the whole graph of this is the graph of the solution. No, it's very important to figure out or keep into consideration of what the interval of the solution is. The interval of solution, I, becomes the domain of this one. So if I is from 0 to infinity, you are only taking this portion as your solution. If this is this one, negative infinity to 0, only this part is the solution. It's from, let's say, 3 to 10, it's only this part is the solution. So your solution is, in general, only a portion of the whole graph. Unless, of course, if you didn't have anything like this, you could have picked I to be the whole real line, but in that case, the whole thing would be the graph.
And between negative infinity to 0, shouldn't it be below the x-axis because the graph is...
Also, you're right, the negative infinity to 0. Correct, of course. It's this one. So, right? Negative infinity to 0, the graph is this one, which is below the x-axis.
Can't we join the intervals, like from 0?
No, I mean,
0 union.
but then in that case, it's not an interval anymore. So you see, like when I say interval, it must be one piece that connects. Another definition. Now let's consider an ordered linear differential equation. So this must be an equation containing the ordinary derivatives of y up to the nth degree. So let's say that this is the relationship between them. This is x, y prime up to the nth derivative equals 0. So it is the function, it is the relationship between them. So for example, in this case, f is put tan inverse x to the other side, then it would be this one, the whole thing. Let's call this slide again. Now, a solution of this equation, a solution of star, okay, containing n is the order here, and arbitrary constants. It is called general solution. So if you are talking about the second order equation, then you must have two arbitrary constants if you are trying to find a general solution. Okay, a solution of, again, star obtained from the general solution. By choosing certain values of the constants, actually I should say arbitrary constants, is called a particular solution. And finally, a solution that cannot be obtained from the general solution is called a singular solution. A solution that cannot be obtained from the general solution is called a singular solution. So we have three types of solutions: general one, particular, and singular. The general solution is the solution that has arbitrary constants in it. The number of arbitrary constants is always the same as, must be the same as the order of the equation. Particular solutions are the ones that you obtain from the general solution. And singular solutions, like the name says itself, they're singular, they're away from, they cannot be obtained from the general.
So what is this? If you're saying y is 1 over x is solution.
Yeah, I cannot say anything because this is just a solution, but what you can say is at least it's not a general solution,
Not.
because there is no arbitrary constant.
What are the arbitrary constants?
Okay. Next example. Actually, you're not very, you're kind of familiar with arbitrary constants. It's like, see, when you take the integral, right? You get an arbitrary constant. It's like that. But anyway, show me an example. Okay, let's have a look at this differential equation. Okay. First of all, let's classify this. This is what's the order of this equation? It's a first order, right? We have dy dx on it. It's a first order ordinary differential equation. Is it linear or non-linear? Non-linear. So this is a non-linear ordinary, first order ordinary differential equation. Now, the family of functions given in this form, phi of x equals x plus c squared, and c is free here, is a general solution of this equation. So first of all, let's prove this claim. Okay? So I claim that the functions defined in this form, x plus some number squared, these are all solutions to this differential equation. This is very easy to justify. If this is phi, what's phi prime, what's its derivative? The derivative is 2 times x plus c. So when you substitute phi here into the equation, you would get phi prime, right, squared minus 4 phi. This is, now phi prime is this one. So this is 2 times x plus c all squared minus 4 times phi. Phi is this? X plus c squared. And what do you get from this? Zero. Right? This becomes 4 times x plus c squared minus itself. This is always 0. No matter what c is.
Does it change or are you always putting it?
No, I mean, this is true for any value of c because in the end c cancels out. So this shows you that this is a general solution. It's a solution, first of all, this shows that it's a solution. Why is it a general solution? Because it has an arbitrary constant in it. Now,
So arbitrary constants are the already like the numbers that are like already.
The numbers that you can choose, that any real number. Now, by choosing particular, like by choosing certain values of this number c, you'll get the particular solutions. For example, if you choose c to be 0, you would get phi is x squared. And if you choose c to be 1, you get phi equals x plus 1 squared. If you choose, let's say, c to be -1, you'll get x minus 1 squared, and etc. Of course, like you can keep doing this. You can easily check that these are also solutions to this differential equation. And you can check it by hand, but you'll see that it's true. Therefore, these are also solutions, but these are the solutions that are obtained from the general solutions.
So that's why I call it general, because it can take many forms.
Exactly. Therefore, now these are called the particular solutions. Of course, you have infinitely many particular solutions. For each value of c, you'll get a particular solution. Okay, do we all agree so far? Now, I claim that finally, y equals 0 is also a solution of our differential equation. Okay, why so? When y equals 0, this is also a function, right? This is the constant function. If you're at 0 here, 0 prime is 0. So square is also 0. You get 0 minus 4 times 0 is 0. It's correct. So this is the solution. Now, the question is, can we obtain this solution from the general solution? Now, in other words, will x plus c squared be ever 0? Now, if this is true, this will only happen if c is negative x. But this makes no sense because c is a constant. But x is a function. How come a function can be, how come a constant, which by definition never changes, be a variable? It's impossible. Let me put actually variable, maybe it can be easier to see. Therefore, you cannot obtain this solution from the general solution by playing with the values of c. In other words, no matter what you choose c to be, you'll never get the solution 0. It means that y equals 0 is a singular solution.
But it isn't a solution.
It is still a solution. Yeah, of course it's a solution, but you just name it as singular solution.
Like an exception.
And I'll leave this for you to check at home. I claim that this family of functions, c1 times sine 3x plus c2 times cosine 3x, here c1 and c2 are arbitrary constants. This is a general solution of this equation. Y double prime plus 9y equals 0. This time you needed 2 arbitrary constants because your differential equation has order 2. And by playing with the values of c1 and c2, you will get particular solutions. For example, if you choose, let's say this to be 1, this to be 5, then sine x plus 5, sorry, sine 3x plus 5 cosine 3x is a particular solution, etc. have a differential equation, like this one, like the other ones, usually you have infinitely many solutions. In other words, you'll have a general solution, and in the general solution there will be an arbitrary constant. Therefore, by choosing different values for that constant, you get different solutions. But if you have a differential equation with some extra given conditions, maybe you will be able to find the values of these constants. And an equation like that, a differential equation with a certain set of conditions, is called an initial value problem. So let me write it this way for you. An initial value problem, and this I refer as IVP in the future. Has the following form. Oh. I write it in the Leibniz notation. The nth derivative is equivalent to f of x, y prime up to the n minus first derivative. It's important though, okay, the nth derivative, the highest derivative, is separated from the rest. Okay. Solve this equation subject to, in other words, solve this equation under these conditions. Y of x0 equals y0. Y prime of x0 equals y1 up to y n minus 1 x0 equals y n minus 1. So this is the differential equation. These are the extra conditions. By the way, how many conditions do you have here? Three? No, I mean, I did like 3 dots here. You have n conditions. You select this is the first condition, this is the second condition, and this will be the nth condition. You need n many conditions because this is an equation of order n. And here, what is x0? X0 will be a point from the interval of solution. And usually you are using this, actually I should say these conditions, depending, because usually you have more than one, to figure out the values of those constants. And actually you're not unfamiliar with this. You already talked about initial value problems, the first order initial value problems in Calc 1 and in Calc 2. I'll give you an example. And then you'll remember it. For example, this is an IVP, it's an initial value problem. Right? You have derivative on one side. This is the highest order derivative anyway, is equal to some function. And this is your condition. You only need one condition because this is an equation of degree 1. So this is an IVP.
So it was like.
If it was the second derivative here, you would have to have one more condition. Yeah, you would have 2 conditions. If it was degree 2, you would have 3 conditions. And how do we solve this? Let's solve this very quickly. How would you solve this equation? You want to get rid of the derivative, so you have to take its inverse, which is integral. So you can integrate both sides. Of course, the integral of 2x is x squared, but it comes with an arbitrary constant. Therefore, you select, if you didn't have this extra condition, this will be your general solution. But now we have this condition, y of 1 equals 4. Well, what does it mean? This means that x is 1 and y is 4. Then you substitute these into this equation to find the value of c. So you get 4 equals 1 squared plus c, which implies that c is 3. Therefore, our solution is x squared plus 3. And we're done.
Professor, why did you write there, like, function of x or y or all of these?
Here?
Yeah.
Yeah, because I mean, the right-hand side will be a function. Yeah, of course, I mean, because you don't know what you have on the other side. So here, basically what I'm saying is the high order derivative, the highest of the derivative must be on one side, and everything else must be dumped into the
Even
other
if you
side.
have also derivative on the other side.
Yeah, of course.
It's not just restricted.
No, this is like the easiest example.
So that's why it would be a -1.
After the n minus first derivative. Okay, for example, let's say we get some y prime equals y with y of 0 equals 4. In other words, you want to solve this condition, so you want to solve this equation subject to this condition. If it's an initial value problem, you need, I mean, you only have one condition because you have only the first derivative here. And for example, how can we solve this? Again, this is too difficult. What is y prime? Y prime is dy dx equals y. Cross multiply this. In other words, collect the y terms to one side, x terms to the other side. Then you will get dy over y equals dx. By the way, before we solve this, can you guess the solution or solutions to this equation? In other words, do you know a function whose derivative is itself?
Yes.
E to the x. So for example, e to the x will be a solution. Are there any other?
Constants.
Not all constants. For example, if y is 5, 5 prime is not the same as 5, because 0 is not 5. But a constant times e to the x is also a solution. For example, 5 times e to the x is also a solution. Okay. So we should be, in our final solution, there must be e to the x. Now let's solve it. Okay, we got dy over y is dx. Now you can integrate both sides. Okay. What was the integral of dy over y? Remember, this is logarithm y. The integral of the other side is x plus some constant. But then you want to get rid of the log here. To get rid of that, you should apply its inverse. And remember, the inverse of logarithm is the exponential function. Therefore, e to the logarithm y is equivalent to e to the power x plus c. But I can now split this into two. You can write this as e to the x times e to the c. Now, keep in mind that c is a constant. If c is a constant, e to the c is also a constant. So instead of writing e to the c, we can write a new constant. So instead of this, let's say write capital C. And e to the log y, as I said, it is simply 1. And you don't even have to write the absolute value anymore because e to the x is always positive. So we can just write it this way. So y equals, I'll write the constant first, c times e to the x. And what type of a solution is this? And we say general solution because it has an arbitrary constant.
The complexity of the question will be by the integral side.
That's it. Now, if we didn't have this condition, this would be our general solution. And of course, this defines a family of functions. For each value of c, you get a solution. So for example, if c is 1, you get y equals e to the x. If c is 2, you get y equals 2 times e to the x. for example, if c is -1, you get y equals negative e to the x. If c is 0, it can be 0, then you get y equals 0, which is the x-axis. It's also a solution. Now, we use this condition to figure out which one of these solutions is actually the solution to this IDP. Of course, if y of 0 equals 4 simply means that x is 0 and y is 4. Put them into the solution. So 4 equals c times e to the 0. This means that c is 4. Therefore, your solution, this is the only solution to this equation, is 4 times e to the x.
What
Please,
happens?
yeah, for one time. Can you just repeat it?
Now you use this condition. This says when x is 0, y must be 4. So I just substitute 0 here for x, and for y you substitute 4. So you get 4 equals c times e to the 0. E to the 0 is 1, so c is 4. Once you know c, you put it back in here, and you get your only solution.
So particular.
Well, it's not actually a particular solution, because in this case there's only one solution.
So it's just
Just a solution. But now, as we see, we look at some examples, like for example, this one, where you have, for example, we have this equation without this extra condition, you have infinitely many solutions. You look at the equation matrix, you have only one solution. Last class I showed you, I remember writing in the last minute, writing an example of an equation, remember the differential equation, which had no solutions whatsoever. So now the question is, whenever you have a differential equation, in particular whenever you have an IDP like this with some condition on it, when do you expect to get a unique solution? In other words, when do you expect to get only one solution? And this is answered in the next theorem. I would like to give the proof of this theorem, but this proof is very, very technical, beyond the scope of this course. But I'll explain the theorem, and I'll tell you how to make use of the theorem, because you should know how to apply it. This one only works for the first order IDP. So consider this. dy dx is equivalent to f of xy, subject to this condition, y of x0 equals y0. Now, here is the condition. If, write it short, if f is the function here, if f and df dy, okay? This is the derivative of f with respect to y. If these are both continuous, on some rectangle around this point, okay, if you want, I can even write it in technical terms. For example, how can I define a rectangle around this point? You can define it like this. Let's say the set of all xy is such that, I'll draw a diagram to visualize this. This is less than a, this is less than a. If f and its derivative with respect to y are both continuous on some rectangle around this point P, then the theorem tells you that there is a unique solution to this differential equation. Let me write it short, to star. With star, I mean this IDP.
Why rectangle? Or is it just
That's because for the proof of the theorem, we need the rectangle. And again, whenever you talk about the solution, remember you always impose an interval. And then we write here where is that interval on some interval I. I'll write it this way: the set of all values of x minus x0 is less than or equal to h, and h is less than. This statement might look a little bit confusing, but it's very easy to apply. But before that, let me explain it over the diagram. This is what the theorem is simplifying here. Say that you are checking out an IDP like this. You want to solve this equation under this condition. Now, with x0, y0, you define a point on the plane. Let's say that this is the plane. This is the point. So this is x0 here. And this is y0, this is x1. The condition is if f and its derivative with respect to y are both continuous around on a rectangle around this point. And I define it this way. Now, what does it mean? If the absolute value of x minus x0 is less than a, this means that x is between x0 plus a and x0 minus a. So it's like this. This is x0, this is x0 plus a, this is x0 minus a. Similarly, this means that y is between y0 plus b and y0 minus b. Here is y0 minus b, this is y0 plus b. So where is the rectangle? And there it is. So this is a horizontal line. So is this one. So is this one, and so is this one. The rectangle is here. So if f and its derivative are both continuous in a rectangle like this, then what we are saying is you always get a unique solution to this differential equation inside this rectangle. In other words, that you will be able to find a number h which is less than a. Again, this means that x is between x0 minus h and x0 plus h. So here is x0 minus h, here is x0 plus h. So you expect to get a unique solution on this interval. So you have, let's say this is your solution. Say that this is your solution. And that would be one and only one solution inside of this rectangle. Let me give a concrete example and you'll see that it's pretty easy to apply. Let's check if I'll get you a bunch of IDPs and let's try to determine how many solutions would we expect. Let's start by this one. dy dx is x cubed plus x y cubed minus, actually let me keep it simple this way, under this condition, y of t equals 1. Before we go into anything right else, first of all, let's figure out our point. What is the point in this case? Point is 2, 1. In other words, you want your solution to pass through this point. Now, and what is f? This is f. F is, you select this function on the right hand side. So in this case, f is x cubed plus x y cubed. Now, what is fy, or you could write the f dy? This means the derivative of f with respect to y. In other words, you differentiate this function, but you treat y as your variable. In other words, you'll treat y as a variable, therefore you have to treat x as a constant. So when you're differentiating this, because you treat x as a constant, x cubed is constant, therefore its derivative is 0. And when you differentiate this, this is x times, so this x will stay. You only differentiate y cubed, from which you will get 3y squared. So it will be 3x y squared. No, you take the derivative with respect to y. So dy is 1. So we get these two, but if you look at these functions, these are both polynomials. And polynomials are continuous everywhere. In particular, these two will be continuous on this interval. Okay. This one and this one are continuous. It's not enough for these functions to be continuous at this point only. They should be continuous around that point. That's why you need a rectangle. Okay? So these are both continuous around the point 2, 1. Therefore, by our theorem, this initial value problem must have a unique solution. By theorem, there is a unique solution. Now, if I'll stop here, I won't give any more examples, but if, for example, f or the f given, if one of them or both, if they were not continuous around this point, you cannot say that you don't have a unique solution. What you can say is you cannot use this theorem because the conditions are not set.
So there is another theorem.
Then you have to try something. Now, I'll stop here. Before you leave the classroom, please take, I prepared some questions for you. Okay, please take 2 of these. We have 2 pages. It's front and back, by the way. There are a bunch of questions here, and this covers pretty much everything that we did this week. So I would suggest you go through these this week.